in the laboratories. Chris Quigg at Fermilab, Bob Kahn at Lawrence Berkeley Lab, and Bill Marciano at Brookhaven guided me as I began my career. The postdocs I've worked with at the labs are too numerous to name, but they provided inspiration to me and enthusiasm, and they've gone on almost uniformly to have successful careers. My research focuses on theoretical calculations of the predicted experimental signatures of the Higgs boson. With its discovery in 2012 at the Large Hadron Collider at CERN, the Higgs bosons become a tool for searching for new properties of nature. Particle physicists are convinced that we only understand a small part of the subatomic world. Questions about the nature of dark matter and the sources of particle masses are central to our exploration of particle interactions. And precision studies of the Higgs boson, such as those I do, and the properties of the Higgs boson play an important role in understanding the new interactions of particle physics. As the LHC accumulates ever more data, however, the requirements for theoretical calculations become ever more demanding, requiring sophisticated mathematical techniques and computer algorithms. Practically speaking, these calculations require a dedicated team, and this fellowship will allow me to enhance my team. High-energy physicists in the U.S. have a unique tradition dating to 1982. Every few years, we get together as a community to discuss the state of particle physics and where our field is headed. In the early years, these meetings were every 2 years and occurred for 3 weeks in the summer in Snowmass, Colorado. Over time, the frequency and location has varied, but the goal has not. The goal is to have as broad a cross-section of scientists as possible get together and hash out physics questions and possibilities for future experimental directions. Theoretical calculations are a crucial ingredient of these deliberations. At these meetings, we do not set priorities, but discuss the theoretical and experimental issues. This framework of intense discussion is called the Snowmass process. The U.S. high-energy physics community is about to enter another round of the Snowmass process as we consider what the experimental program in the coming decades might be. This award will enable me to hire postdocs to work with me on the difficult theoretical issues connected to Higgs physics and precision calculation, and to contribute significantly to the discussion of the physics issues relevant for determining the next steps for our field. It's an exciting opportunity for me and for the theory effort at Brookhaven. Thank you.
All right. At this point, I'd like to welcome Dr. Ian Foster to the stage. Dr. Foster is from Argonne National Lab, and his award is for trailblazing work in distributed and high-performance computing with fundamental and long-lasting impacts on both computer science as a discipline and the practice of computing across the Office of Science.
Okay, it's a long time since I gave a talk without a dozen overheads, but I'll see what I can do. Thank you very much, Dr. Fall, Dr. Weatherwax. I'm very appreciative of this very generous award. For me, coming here, I feel like I'm coming to the headquarters of the world's greatest scientific organization, but today I learned that it's officially called the Borg. Okay, so I'd like to first of all thank the Office of Science, and in particular the Office of Advanced Scientific Computing Research, who have supported me for 30 years at Argonne National Lab. So from my perspective, I applaud their good taste in the research that they support, but also their sustained commitment to computation as a tool for discovery. I'd also like to thank my colleagues at Argonne National Lab, who have created what, in my view, is the greatest lab in the world in which to advance science by developing advanced computing technologies and applying them. I see this award as a recognition of what many people at Argonne have developed over many years, dating actually before I arrived in 1989. So I originally came to Argonne to work in automated reasoning, which is an early form of AI, but in a story that I think captures part of the magic of the national labs and DOE, I became bewitched by the potential of what at that time were very new high-speed networks and parallel computers, and their potential as discovery tools. So this fascination led me to pursue oddball topics like parallel program design and grid computing, on-demand computing from light sources, parallel climate models, speed of light data transfer, and many other things as well. And in the process, I gained a deep appreciation of the power of well-crafted software and the audacious experiment as tools for both learning and communication. And also, I learned how important it was to be able to work with brilliant scientists eager to do something new in whatever application domain they are working. So now, 30 years later, computing is, again, in my view, at a very exciting time. We have, of course, massive data at a volume that we previously could not even conceive of, pervasive and very powerful artificial intelligence technologies, exascale simulation, soon to be with us, terabit networks, edge computing, new accelerators, both particle accelerators and AI accelerators. These and many other new technologies all demand, in my view, that we rethink once again what computing means for science and how computing, data, experiments, and people can be linked at the speed of AI-accelerated thought to both solve old problems and new problems far faster than before. To make progress in this new world, we need, in my view, new concepts, design principles, methods, technologies, and above all, new audacious experiments and partnerships in order to help shape the scientific environments of the 2020s and beyond. So my goal with this very generous fellowship is to pursue such questions. I want to engage the computing community writ large, both across the labs and in the university community, to imagine how science can and should be different in this new world, to examine what hardware, software, and data systems may be required to support new ways of doing science, and to conduct experiments to establish the feasibility of new approaches. In my statement of work, I coined the term Project Celerity to capture this goal of enabling connections at the speed of thought. One area of great interest to me is the use of AI methods to drive autonomous experiments. Computers, whether running spreadsheets in the old days, climate simulations, or AI agents, they are basically cognitive processes that, by automating the routine, allow us to think more freely. So I actually started as a chemistry major, but left for computing because I was both bored by and very bad at titrating things. So I'm well aware of how mind-numbingly routine much of experimental science can be. And I know from talking to material scientists just how challenging the materials design problems are that they want to undertake. They urgently need cognitive prosthetics to which they can hand off problems like identifying candidate materials for low-cost, high-density, long-life batteries. That could be the next Nobel Prize. An autonomous lab that could choose the next experiment or simulation based on an AI agent's estimation of where new knowledge will be most valuable could be transformative. So such a system would need really interesting new capabilities, new computing capabilities, data capabilities, software systems, as well as experimental apparatus in order to realize it in practice. Another area where what you might call an AI-first approach to science demands new approaches relates to simulations. So Moore's law is slowing, so we can't keep counting on a bigger computer to run the next larger simulation. At the same time, deep neural network technologies are growing in sophistication. So it seems to feasible, at least, to think about AI-enabled approaches which construct neural approximations to functions so that rather than handcrafting these approximations, we can learn them from examples. And in areas like climate science, material science, many others, I think we need to explore the feasibility of accelerating simulation codes by embedding learned function accelerators within them. So again, AI embedded in science, we need new computing, data and software systems to realize this potential. And a third area, final area, I'm going to stop soon, of promise relates to the data deluge. So just to give one example that I am familiar with, the advanced photon source upgrade will soon generate 3 orders of magnitude more data, with automation probably increasing that amount yet further. Environmental and observational observatories present similar data challenges. Discovery at the speed of thought requires that this data be collected, processed, and compared with simulations or experiments in order to maximize the value of the next observation. So again, fascinating new requirements for computing data and software. So this project that I envision, of course, isn't going to solve all these problems by itself. They're much too vast and encompassing. I hope indeed that the Office of Scientific Computing Research, as well as other offices within the Office of Science, Basic Energy Sciences, Biological and Environmental Research, Nuclear Physics and others, as well as the new Artificial Intelligence and Technology Office, will tackle these problems in their programs. But in the meantime, I aim in this work to engage the community, to contribute to the framing of the problem, and to demonstrating how computing at the speed of thought can transform how science is done in the 21st century. So let me express one more time my thanks for the recognition and honor that you do to myself, but also I think to the Office of Scientific Computing Research and Argonne, and say thank you again. Thank you.
At this time, I'd like to welcome Dr. Joshua Freeman to the stage. We did. Dr. Freeman is from Fermi National Accelerator Laboratory, and his award is for pioneering advances in the science of dark energy and cosmic acceleration, including leading the Sloan Digital Sky Survey supernova study, co-founding the Dark Energy Survey, and service as its director.
I have one visual aid. I'm giving all my money to Ian. Sorry, no. Okay. So the universe is a very old place. If you compressed 14 billion years of cosmic history into just 1 year, a human lifespan would be about 0.2 of a second. So when I was in college 1/10 of a second ago, I went to a talk by a famous cosmologist from Cambridge named Dennis Sciama, and he described the history of the universe starting from the present and going backward in time. And by the end of his talk, he was discussing the first tiny fraction of a fraction of a fraction of a second after the Big Bang. Those were real seconds, not these compressed seconds. And I was hooked. I realized that cosmology was like archaeology on the grand scale. Instead of using pottery shards to reconstruct an ancient civilization, cosmologists could use observations of the universe to reconstruct the beginning of time itself. I knew then what I wanted to be when I grew up. Now, at that time, cosmology was undergoing a renaissance. Physicists had invented new theories of the elementary particles produced in powerful accelerators at places like Fermilab and CERN. But those theories also predicted what would happen just after the Big Bang, when the universe was very hot and dense, and particles were colliding with energies even much higher than those in accelerators. So we realized we could use the early universe as a laboratory to constrain those theories in a complementary way to the accelerators. And this synergy between particle physics and cosmology has been a major theme over the last 40 years. So really, through this lecture by Dennis Sciama, I had, like Forrest Gump, wandered into the right historical place at the right historical time, completely by accident. Now, a couple of years later, I went to graduate school to study cosmology, and I chose the University of Chicago, where I now teach, because it had 2 cosmologists on the faculty, whereas all other schools had 0 or 1. So cosmology was a very small field at that time. And James Peebles, who was a leading cosmologist at Princeton, who was awarded the Nobel Prize just last week, he was the cosmologist at Princeton for many decades. So really, this was a field that really mushroomed in the 1980s and 90s and in the decades since. Now, when I was a graduate student, there was a famous cosmologist at Chicago named David Schramm, and he convinced Leon Lederman, who was then the director of Fermilab, to broaden the lab's high-energy physics program to include theoretical astrophysics to really develop this growing synergy. Now, David was a former national wrestling champion. Many of you know he was quite a presence and could be very persuasive. And let's just say Leon was a comparatively small man. And so the rest is history. And I later joined the Fermilab Astrophysics Group as a staff scientist and have been there for the past 30 years. Now, like most cosmologists at the time, I was a theorist working on models of the early universe, but we were frustratingly data-starved. So it was often difficult to tell which theories were really going to be more promising than others. And as a result, many of my colleagues in particle physics looked down on us as kind of idle speculators, untethered from the real world. But that situation soon changed dramatically. Following this cosmology theory boom of the 1980s, observational cosmology has undergone a real explosion, and we're now swimming in an ever-growing sea of cosmological big data. In partnership with other national labs and universities, Fermilab has played a central role in igniting this explosion. And the Office of Science's Office of High Energy Physics now recognizes the cosmic frontier as a major research thrust within high energy physics. By the way, this explosion has now attracted many particle physicists into cosmology. They no longer look down their noses, and in fact, they want to get in on the action. Those of us who have been in the trade since our youth call this syndrome adult onset cosmology. And so sensing this cosmic tidal wave of data would finally allow us to test our theories, I've broadened my research program over the last 20 years from theory to include observations with cosmic surveys. And through its national labs, the Office of Science's Office of High Energy Physics has really been in the vanguard of these surveys and has made them possible. And I really think the willingness of the DOE to follow its scientists into such new modes of discovery is a tremendous strength of the system, and one that I've benefited from directly. This willingness and support enabled us to harness the resources and brainpower of the labs to create a new project, the Dark Energy Survey. At Fermilab, we built a 570 megapixel camera and installed it on a telescope at Cerro Tololo Inter-American Observatory in the Andes Mountains of Chile. Happens to be an NSF facility, but that's fine. And in the process, we organized and hosted an international collaboration of over 400 scientists who are engaged in this project. This image shows one of the first pictures we took with the Dark Energy camera on September 12, 2012. I remember this night well. I was connected by video conference to the control room at the telescope, and while the team was taking this image, I was in the aisle of our local supermarket with the smartphone to my ear, searching for Pop-Tarts for my daughters. And one of them, Sarah, is now here as a freshman now at George Washington University, and she's here with us today. I'm pretty sure I'm going to be the only person talking about Pop-Tarts today, so I wanted to get that in. So this picture is really a small part of a much larger image, and it shows this beautiful spiral galaxy, which I'm sure you all recognize as NGC 1365, right? Everyone knew that already. Like our own Milky Way 1365, NGC 1365 is about as hard to say as Distinguished Scientist Fellows, I think so. I'm just going to call it 1365 for short. Like our own Milky Way, it contains billions of stars, like our sun, and it's just one of billions of galaxies that are visible with telescopes across the sky. Over the next 6 years, we used the dark energy camera to carry out a survey of 300 million galaxies over 1/8 of the sky. And this camera has also been used by astronomers around the world to make other discoveries, such as many new moons orbiting Jupiter. In the 1920s, Edwin Hubble and others discovered that the universe is expanding. Galaxies like 1365 are moving away from us, and more distant galaxies are moving away faster than those nearby. Now, since gravity is attractive, we expected, and our Milky Way is tugging on 1365, we expected the recession of these galaxies to be slowing down over time. But in fact, we now know that tomorrow, this galaxy is going to be moving away from us slightly faster than it is today. The expansion of the universe is speeding up, not slowing down. This cosmic acceleration was discovered in 1998 by 2 teams of astronomers studying supernovae, exploding stars, using an earlier, smaller camera on that same telescope in Chile. One of those teams was led by scientists at the Office of Science's Berkeley National Lab, who shared the Nobel Prize for this discovery several years ago. We don't know why the universe is speeding up. We don't think it has to do with the fact that we are driving these galaxies away on a personal basis. So we have a good hunch that the culprit is something we call dark energy. Unlike all other forms of matter or energy we've ever seen, dark energy is gravitationally repulsive. So it pushes galaxies away from each other. And we now believe that dark energy constitutes about 70% of the universe. So we embarked on this dark energy survey with support from the Office of Science and the Office of High Energy Physics to address this fundamental question. Why is the expansion of the universe speeding up? What is the nature of dark energy? It turns out that taking pictures of 300 million galaxies is really one of the most powerful ways to address this puzzle. So this is just one of those 300 million galaxies, and I think I have slides showing the other 299 million, but we probably don't have time to go through. I've only got a nanosecond left. So we don't know the answer to this question. Although the Dark Energy Survey collaboration, we've already written over 250 papers for publication, we're still analyzing the data to pull out these very subtle effects of dark energy. I plan to use this Office of Science Fellowship Award to support students and postdocs at Fermilab and the University of Chicago to collaborate with the rest of our colleagues to carry out this analysis and really try to uncover the nature of dark energy. And other DOE-supported surveys starting now, such as the DESI project, and in the next few years, the LSST project, will provide even further clues to this mystery. So it's a privilege to be part of this collective endeavor. I'd like to thank the Office of Science and the Office of High Energy Physics for its support for this award and for its continuing support of our curiosity-driven basic research at the national labs. They're delivering remarkable discoveries about the universe and enabling rewarding and fulfilling careers like mine. I'm humbled and honored to be in this company and looking forward to the many discoveries yet to come. Thank you.
At this time, I'd like to welcome Dr. Barbara Jasek to the stage. Dr. Jasek is from Lawrence Berkeley National Laboratory, and her award is for leadership in discovering and characterizing the hottest, densest matter in the universe, the quark gluon plasma, and in building collaborations and mentoring scientists at the frontiers of nuclear physics.
So my first instinct, standing up here, is to offer to yield my time to Josh and see another picture. But I'll do my best. It's a tough act to follow. I want to say thank you to the Office of Science and to the Office of Nuclear Physics for your support over these many years, as well as for this award. The Office of Science has an extremely important role as the steward of both fundamental physics and accelerator science and technology. And your long-term support of these areas and the people who do them allows us to accomplish some really great things that a year-by-year planning would just not allow at all. We also have the opportunity and the privilege to train many young scientists who then go on to be the next generation of leaders, but also innovators, technological wizards, and the inventors of the future, and not just in basic research. And I think that's a big part of our mission. All the way back to the days of Ernest Lawrence, fundamental physics and accelerators were the original capabilities of the science labs. And your sustained support in these areas has really served the country well and continues to do so. We appreciate it, and our students and postdocs appreciate it, and we want to give back. I'm honored and very proud to be part of this endeavor. So looking forward, the electron-ion collider will be the next great example of this kind of sustained support. We're going to discover some fundamental truths about protons, neutrons, and nuclei, and about the properties of strongly interacting quarks and gluons. I'm going to say a little more about that in a moment. But I like to think of the adventure that's going to start with the electron-ion collider as writing some 21st century just so stories. You know, how the proton got his spin, how the neutron got her mass. So we at Berkeley are looking forward to working with the Office of Nuclear Physics and the Office of Science to make the EIC and the science a reality. Before I talk a little more about the science, though, I want to say a few words about the partnership between the national labs and the universities. The labs are fantastic places, as you all know. At the labs, one can do very, very large range of projects. You can do individual investigator projects, and you can do some really large-scale projects that require multidisciplinary teams and superb technical infrastructure. In my experience, our teams are physicists and engineers and chemists, and we can do some things that individuals or even subsets of one area couldn't do alone. One of the things you almost never hear about is that team science, besides letting you do big stuff, it's also really fun and exciting. And that, I think, makes us more productive and inspired. You can do things at the national labs that you can't do anywhere else. But when you add students to the mix, some real magic happens. A typical first response for a student, newly encountering a national lab environment is, "This is awesome." I hear that a lot, and it's great. Then, of course, the questions come. Why this? Why that? Why? How come? How? And those questions actually cause us all to look at what we're doing in a fresh way. And I think that's where the overlap between the national labs and the universities are something really special. And the fact that the labs welcome that and have a space for the students, I think, is to everyone's benefit, including the labs. And I think that's how so many innovative ideas and technologies and approaches come up. The combination really makes both the labs and the universities better at their mission. Now, some of the discoveries that we make are the answers to the scientific questions that we started out asking. But many of the other discoveries are the things that we have to invent in order to be able to answer the questions. And those are those accidental inventions that go on to be things that become the everyday tools we use later, like the World Wide Web, whose inception I remember very well. Also, learning how to do things as a team is a discovery process as well as a skill. The sustained support from the Office of Science that I've enjoyed has been truly awesome. It's let me undertake really long-term projects and work with the young scientists to teach them how do you do something that takes, 10 or 20 years. And, 10 or 20 years. Anybody here ever built a collider detector? That's really the time scale we're talking about. And that requires a knowledge that the commitment and the resources are going to be there so that your time is invested in the right way. Of course, it's also an investment of the treasure from the taxpayer, and we really appreciate that and appreciate the stewardship of the Office of Science for letting us do that. So now, of course, is the stage where I would like to launch into a 25-minute lecture about why the hottest matter on the planet is so exciting. In a way, it's the exact opposite in distance scale or size scale from what you heard from Josh. But really what we're doing with this very hot, dense matter is looking at that first microsecond after the Big Bang. So, and we still have an interesting debate going on, which is going to continue, whether cosmological observations now have any sensitivity to correlations on the scale of 1 femtometer early on. How do we see those and things we can observe now in the cosmos? Now, it turns out that the quark gluon plasma is much more interesting than we expected. How can something so hot, trillions of Kelvin, behave like a liquid? This was one of the biggest surprises that came out when we turned on the relativistic heavy ion collider at Brookhaven some years ago. And it turns out that even at that temperature, the strong interaction remains really strong. And so what we have is a system where many-body physics dominates. And so the attractive interaction among multiple particles is as strong as the repelling interaction that comes from the super high temperatures and things flying out at half the speed of light. It's interesting to note that the many-body physics problems are really at the forefront in many areas of physics. Our plasma behaves a lot like the warm, dense matter that plasma physicists have to deal with. When you try to do fusion, a lot of the issues that make it difficult, that cause interesting asymmetries, well, they're interesting to us. They're not so interesting if you're trying to reach ignition. Those also come from the many-body physics in the warm, dense plasma. And I think there's a lot of room for cross-fertilization. Similarly with cold atoms and with strongly correlated condensed matter systems, and there is a lot of intellectual exchange, and that's very exciting. And a lot of that is because of the proximity of people at the national labs. So I think that there's a lot of opportunity for the different areas to teach each other and learn from one another, and that's really exciting and keeps the young people coming into science instead of all wanting to go make films. Some of them even make films about science, which is really cool. So this fellowship is going to allow me to take the next step and find out how many of the very interesting and weird properties that we see in very hot, dense matter that's full of gluons, what happens when you have very cold, dense matter that's full of gluons? My bet is that it's going to be just as weird and surprising as hot, dense gluonic matter. And so I look forward to hiring postdocs and students to work with me on devising the right set of experiments, right set of measurements at the new electron-ion collider to find out about cold, dense matter. Thank you very much for making it possible.
All right, I'd like to invite Dr. Jose Rodriguez to come up. Dr. Rodriguez is from Brookhaven National Laboratory, and his award is for discoveries of the atomic basis of surface catalysis for the synthesis of sustainable fuels, and for significantly advancing in situ methods of investigation using synchrotron light sources for individual researchers and for consortia.
First, thank you very much for the introduction. I am really happy to be here to receiving this award. Today I'm going to be talking mainly about the uses of synchrotron in catalysis and how you can use a synchrotron to actually understand how a catalyst works. Catalysis is a very important process that you actually have in many of the chemical processes in the industry. For example, the fabrics over here is produced by a catalyst. Over there you have this plant here, this is synthetic plant, is being produced by a catalyst. So practically you will find that catalysis is in every place, is in any chemical, any fuel. So over the years, people have tried to understand how the catalysts work. And the Department of Energy is interested in catalysis because essentially what the catalyst does is that the catalyst accelerates a transformation, a chemical transformation. And when you accelerate this chemical transformation, you reduce the energy, technically the energy that you will need for the transformation. So you really need to understand how this catalyst is interacting with the reactants that you have in a chemical transformation. And this is a very complex thing because, I mean, most of the catalysts that are being used in the industry are complex materials. So you really need to have a lot of tools that allow you to do and see how this catalyst is going to change as a function of time in the presence of a reactant with high pressures and high temperatures, and you have to see how this is going. So the synchrotron actually, with all the techniques that you can get from a synchrotron, like X-ray diffraction, X-ray spectroscopy, and things like that, it allows you to do a testing of how this catalyst is actually working. I have been working at Brookhaven National Lab for almost 29 years. I came in 1990. When I started to work at Brookhaven National Lab, that was the first time that since the Department of Energy have a real interest in using a synchrotron to do a characterization of a catalyst. I remember that I show up after the interview. Norman Sutton was the person that was handling the chemistry department at that time. And after I interviewed him, he asked me, how much money do you need to do this kind of science? And I told him, well, this is a very complex science. I need $750,000. And he looked at me and said, okay, we will see what we can do. Now, you have to realize that Norman Sutton is what we call an inorganic chemist. For him, $50,000 was a lot of money. I was asking him $750,000. So he called Bob Marianelli, that was the person in charge of the catalysis program at DOE at that time. Bob Marianelli was also an inorganic chemist. He told him, well, the boy looks very promising. We want to go into this new area. And he needs $750,000. And Bob Marianelli told him, yes, go ahead and give me the money. So what we wanted to do at that time is that we wanted to study a catalyst on a very controlled environment, in which you actually move from what we call a regular reactor, we move into specialized chambers, in which you actually can control how you have the environment around the catalyst. And we want to put this, what we call ultra-high vacuum chambers, into synchrotrons, and then use all the techniques that you have in the synchrotron to study how was the structure of the material, the electronic properties, and the chemical properties on the reaction conditions. Now, it happens that I don't have a picture of what I am working. However, you can see here 3 pictures of actually are related to the type of work that I do. If you look at the one on the string over there, that's the ultra-high vacuum chamber that I normally use for doing the experiments. That's one type. There is another one that I have here right on the center that's also an ultra-high vacuum chamber. So this is technology that actually came from the NASA program during the space program, and they actually wanted to control the environment around surfaces and in a precise manner. And this is really well for if you want to do catalysis, you actually can put your catalyst inside one of these ultra-high vacuum chambers, and then you can control the environment around the catalyst. And now you can take this chamber to a synchrotron, and then you can actually use the techniques that you have available at the synchrotron for doing structural, electronic, and chemical characterization of the material. So when I came to Brookhaven in 1991, I saw that was a exciting area. The Department of Energy provided all the resources that I wanted to use at that time. And then over the years, I mean, the people in the Department of Energy have changed. I mean, my initial interaction was with Bob Marianelli, D. Stevenson, and Steve Millman. And now these days I'm interacting with Raul Miranda, Chris Fratley, and Vivian Schwartz. But the interest is there. I mean, there is a big interest in the catalysis program of the Office of Basic Energy Sciences to understand these catalytic materials using synchrotron-based techniques, and that's what I have been working. Now, in the last, I think that in 2014, the Department of Energy put a new synchrotron at Brookhaven National Lab. It's the National Synchrotron Light Source number 2. The characteristic of this synchrotron is that you have high intensity and you have a coherent beam. Now you actually can do measurements that are ultra fast. I mean, we actually can do measurements of structural properties and electronic properties in the picosecond regime. And that's very important because catalysis, the fastest that you can go, the best. So now you actually can be doing experiments in which you actually can monitor the properties of a catalyst on the reaction conditions in a very fast way. So the project that I'm going to try to do is trying to do transient or pulse experiments on catalytic reactions, and then use techniques that are available at the National Synchrotron Light Source 2 to study the structural properties, the electronic properties, and the chemical properties of the catalyst on the reaction conditions. The idea is that if you understand how the catalysts behave, how the catalysts actually have the active sites of the catalysts are doing the chemical transformation, then you actually can do an optimization of the catalyst. And then the general picture is that you will minimize the amount of energy that you need to do a chemical transformation. This is a project in which we have been working for about 5 years. Now with this money, we're going to be able to move it forward. It's a project that involves 2 or 3 departments of the Brookhaven National Laboratory. The Synchrotron Light Source is involved. The Center for Functional Nanomateria is involved. The Catalysis Program and the Chemistry Department is involved. And then we have collaborations with people in the University of Kansas, Stony Brook, and Columbia University that also are interested in this type of project. So I think that with the award, we really will be able to move and try to do this pulse and transient experiments, and I think that will be a big contribution. In the spirit of the award, I mean, once that we develop this instrumentation, the instrumentation will remain at the synchrotron, and they will be available for all the catalysis communities. Not only these 5 groups are actually doing it right now. So we are going to be the ones that develop the instrumentation, test the instrumentation, but in the future, the instrumentation is going to remain there, and all the community that is doing catalysis in the United States actually going to be able to do this. So I am really happy that I am getting this award, and I think that it can make a very big push forward in how you actually handle catalysis science in the United States. Thank you.
All right. So now I'd actually like to invite all of the fellows to come up to the stage and take a seat. We're going to move the foliage around. So I think we just heard a lot of really exciting science, a lot of, inspirational discoveries. We heard about Pop-Tarts. I think we're going to hear a lot more. And so Dr. Fall is now going to have a conversation. And you get to start the conversation and ask the questions.
I think the mics are live. My most important question is, how did Dr. Rodriguez understand that these are artificial plants? We really need to have better art. Is that a BER equity, or is that a BES equity? Is it polymers or is it biology? We need better. I
guess that when you come from a tropical country, you cannot see the difference very fast.
All right, great. Well, boy, that was intimidating. You guys are amazing. So I have I've got some questions that folks prepared for me, but I was listening to Josh and thinking back to my own experience, kind of choosing science, which was more or less random. I mean, I ran into somebody who talked about the brain and how the brain works, and I thought, boy, that sounds cool. Maybe I'll study it for a while. And of course, 20 years later, and then I listened to everybody else. Boy, that sounds cool. I'd like to do that, and that sounds really cool. Why is it that we have such a problem? It's a little bit unique to the Department of Energy, or a little bit more relevant to the Department of Energy, communicating what it is that we do to the public and exciting young people to get involved. This is a big challenge that we have, and when I talk about this, I recognize, hey, we grew out of the Cold War, and we spent a lot of our history trying to tell nobody what we did, and now we want to tell everybody what we do. It's not really in our DNA, but maybe I could ask if you guys have any ideas about how to change this equation. I think this is really important. It's certainly a priority of our office, at least while I'm there, to try and raise the awareness of the labs and get people excited about science. Any thoughts there? Go ahead.
Okay, that sounds like it's on. So I want to answer your question by starting with a little anecdotal story. So people at Lawrence Berkeley Lab were building staves of silicon pixel detectors as part of an upgrade for the ALICE experiment at the Large Hadron Collider. The history behind this, it's actually easy to think of. It's a new technology that can improve the way we track the thousands of charged particles that are emitted when you have a collision of two lead ions moving at about the speed of light. And so we built these staves at LBL, and then how do you get them to CERN reliably? These are fiddly little things. The pixels are 26 microns, many individual sensors on these staves. Turns out the most efficient way to do it is to buy them, put them in a nice clear box, and buy them a plane ticket. And then, of course, you have to send somebody along to carry them. And it turns out that the people who are walking through the airport or sitting on the plane with this box of silicon sensors on a stave with all their readout electronics is a fantastic way of outreach. The people who did these transportation runs, and there were lots of them, said that some of them spent the entire flight explaining about how particle detectors work, where the particles come from, why it's interesting, what's quark gluon plasma. And so I think that the answer could be that we probably need to do our outreach in a sort of more visual, a way that people, who live on their smartphones are used to perceiving things, and get the coolness across. Because a lot of times people think, oh, science, that's hard. In fact, my guidance counselor in high school told me, physics, what do you want to take that for? That's hard. So I told him, I don't care what you say, I'm going to take it anyway. And my mother went the next day and gave him what for. But I think we have to counteract that by saying, physics, that is so cool. Chemistry, that is so cool.
And the TSA didn't have any questions about the...
Very good question. So we had all the paperwork, and that was one of the reasons that the boxes were made out of clear plastic, because then it was very easy to see what was inside. And the TSA agents actually think it's cool, too.
All right. You just can't bring your soda with the...
Can I just pick up on what Barbara said? I think I agree with everything you said. I think I think this has been a challenge for particle physics. We can, you can't see elementary particles, so the visuals are challenging. I was showing you a beautiful snapshot of a galaxy. I could have showed you thousands more pictures like that. So there's some parts of our science that are just easier to show as a visual kind of hook to bring people in. But I think there are more ways we can do more, like you were talking about. An example at Fermilab, actually Fermilab in Brookhaven, there was an experiment at Brookhaven called mu(g)-2. It was very successful, and then it was moved to Fermilab and upgraded. And this, basically, they moved this big circular magnet that's, I think it's close to 100 yards across. And again, they didn't put it, they couldn't bring it on a plane, but, they had a big tractor trailer that took, I don't know how many days driving from Long Island to the western suburbs of Chicago. And that turned into a big media event, just transporting this thing across the country. And there's a very sort of famous photograph of it arriving at Fermilab, like in the middle of a thunderstorm. But there were, and it blocked traffic on I don't know how many highways. So people learned about it, and it turned out to be a very effective way to show the public directly in a completely, maybe not totally planned way, the kinds of things we do. So I think we need to take advantage of these kinds of opportunities more. And I think the labs, at least I see it at Fermilab, the labs I think are starting to get more proactive about these ways to really reach out to the general public and also reach down into schools, elementaries, high school, middle schools, to try to excite students and young children about this science. So I think it's starting to happen more, but I think there's much more we can do.
Let me just continue on that. We have at Brookhaven what we call Rick Summer Sundays, the Light Source Summer Sundays. And typically we get about 1,000 people who come for these summer Sundays. And people are really excited to see the cool stuff. So they see the light source, they see the Rick facility, they see the fire trucks with the little kids. But everybody really likes this. And then for weeks afterwards, you'll go to the grocery store and the neighbors will be saying, hey, I was at Brookhaven, I saw such and such. So I think, as I said, this cool stuff, showing that we really have this visual is good.
Let me go back to something that I mentioned. You need to emphasize how wonderful science is to the students that are in the elementary school and the high schools, because that's the next generation that is coming. And I think that is where the battle really is. Because before they decide what kind of career they're going to take, they need to see the wonders of science, and that's going to help them to make a move in that direction. If you impress them when they already have decided what they are going to be doing in life, that's not going to be that much of a difference. They are going to be seeing what wonderful science it is, but they are not going to make a real move into science. I think that we have to make a really strong effort into showing the kids that are in elementary school and the kids that are in high school how beautiful science is and all the marvels that you can get when you do science. I think that that's critical. I mean, we really, if we want to bring the next generation of scientists and we need to bring them on board, we need to do that. I mean, that's critical.
So thinking something concrete we could do is, we used to have lots of high school students at Argonne, for example. I think other labs do. Nowadays we're not allowed to bring them on site. So if we could change that, I think you get them young and early. And we've got some wonderful people working at Argonne who first came as high school students back in whenever it was.
I was just going to say that's true. The paperwork that needs to get done to bring high school students into the national labs is pretty overwhelming.
Is that a new development? Not to work this out in public, but I'm not aware of it. Yeah.
2 years ago, I think.
Huh. That's a great. Yeah, I think, I mean, to your point, you all have mentioned it. There's, maybe your kids and my kids who, see the things I bring home from the labs, the glossy books, and hear about science. There are a lot of kids that don't get that experience. They don't get it by diffusion. And I think the evidence shows that one of the most powerful ways to motivate young people is to bring them into a lab, show them what it means. I see you're a scientist and you don't look so different from me, and I can probably do, yeah, well, no.
Yeah, I mean, what they see at university is probably calculus 101,
That's
and
right.
chemistry 101. It's not creative, and
That's right.
if they can spend a summer at a lab, they learn.
And it's less fun than maybe other things. I don't know. So how about, go ahead, Jose.
So I have one comment on that. My daughter is 14 years old, and she knows that I'm doing chemistry. Okay,
Your daughter, I think you said doctor.
Oh, no, my daughter.
Precocious doctor, right?
Okay, she's 14 years old, and she knows that I am doing chemistry. But okay, Dad is a chemist. Okay, that's fine. And then one day I go back home, and I have an STN image of a surface, beautiful STN image. She have never seen that image. And when she sees that image, she say, "Oh my God, what is that?"
Right.
And then now she's able to make the connection. Okay, this is what Dad is doing. Look at what a beautiful image. And now she really becomes more and more interested in science. And every time when I go home, ask me, "Do you have more images on that?" Yeah, I can give you a full paper on images on that. Do you want to see more images? But now, you see, it's that kind of thing. I mean, sometimes, it's just what we were saying. I mean, calculus is not nice. Chemistry 101 is not nice. The motivation is just not there. But if you find a way, like putting a nice image of the galaxy in the sky, that actually can capture their attention. You have to play with those games. Everything, you have to catch the attention of the child. I mean, that's it.
Right. How about capturing the attention of sort of postdocs? And where I'm going with this is I'd like to get your perspective, and a couple of you sort of touched on it in your comments, about what's really special and unique about the labs as opposed to other places where you could be doing science. So maybe in particular, let's be honest, data science, AI is pretty hot right now. You could probably multiply your salary many times by going to the outside. Not that maybe I shouldn't mention that. What's the, what is?
What factor is it? I
That's
didn't
right.
know.
So the what is special about being at the a lot of paperwork. We talked about the paperwork for the high school students. A lot of overhead, process and so forth. We get that, trying to make that better. But why'd you choose the labs as opposed to and obviously you all have the best of the both worlds in some cases here, but your day job is at the lab. What's the calculation there?
I think for me, the calculation is the labs just have this tremendous, two things. One is just the infrastructure and resources that the labs have. It's not something that a typical university department can come close to. And so the labs can incubate new ideas, new approaches, new experiments in a very dramatic way and really have tremendous impact on the field. The second is that the labs are reservoirs of just remarkable scientific talent. In addition to all the big, great, fancy machines they have, they have thousands of really smart people. And what I found, when I made this transition from doing theory, working with 2 or 3 postdocs or colleagues at a time, to wanting to move into observations where I was working with hundreds of people at a time, having that backbone of scientific talent at the labs was just transformative. You could get a few people, and we did this several times. We would get people working on something completely different, get them excited, usually about some technical challenge, make them realize, hey, what you're working on over here, we could actually take that technology and apply it to this completely different kind of study. You get them excited about it, they get their friends excited about it. They become, in my case, these adult onset cosmologists, and they really, boom, you're off and running. And that kind of thing simply just can't happen at that scale in universities. So it's really, but on the other hand, the universities bring a tremendous amount of intellectual power as well. And so, as you said, it's really that synergy between the labs and the universities that I think is really enabling us to drive these projects forward. So to my mind, it's really the ability of the labs, the resources, the capabilities, the human brain power that is really transformative. And again, everything that's been happening in my field over the last decades would not have happened without the Office of Science Labs.
So you have adult onset experimentalist syndrome.
Right.
So for me, what makes my job fun is sitting down and working with people with interesting problems. So I could be working with someone who's trying to, find where dark energy comes from, or someone who's trying to price an ad campaign to maximize income. And so, of course, the first is just much more interesting, and the people that you get to work with are much more interesting people. So that's why I find the labs exciting. I think that, plus the resources, of course, although some companies have substantial resources too nowadays.
So, go ahead. I was just going to say that the labs have this breadth of effort. You could never find this in a university. For example, Brookhaven, there are people working on neutrinos, people working at the Large Hadron Collider. There are nuclear physicists like Barbara right down the hall from me. So you don't get this breadth, I don't think, anywhere other than the national labs.
The point I was going to add is that a lot of the very forefront technology, the basic science sometimes comes from the universities that leads to that technology, but the real development and nurturing of the technology mostly happens at the labs. The reward system of universities is different, and the kinds of activities that people engage in at the universities are fairly different. I've had the good fortune of having a foot in both camps. At the labs, people are not having to write 100 grant proposals in order to be able to do their science. They can focus a lot on the technology of the doing. And so you have a depth of expertise that's difficult to find at the universities, in addition to what everyone said at the breadth. And that's why I think putting the universities and the labs together is really perfect, because then you get the best of both worlds.
In the area of catalysis, you practically cannot do all the kinds of experiments that we do in the national labs in university because you don't have the tools. I mean, the techniques are not there. You have to combine several techniques, and you will not, it's very difficult to find that in any university. You may find one or two, but then you need 4 or 5 to be able to tackle a catalytic problem. So you practically have to go to a national lab. And you need to work in teams. I mean, people that is coming from material science, people that is coming from different areas, because you have to tackle different problems of the catalytic material. So you really need the environment of a national lab. And there is another thing, in a national lab, I mean, all this research, most of the research that has been done is frontier. I mean, this is really pushing the envelope most of the time. You will not find that in university.
Okay, well, what about, so we're talking about a little bit about the mixing of universities and labs, and I think one thing that's a little bit different about this leadership team, call it at the Department of Energy, is this focus on not just universities and labs, but companies and partnerships, and a real push to try new things. And yet, I think we all feel we're still a little bit straitjacketed by tradition and by the way we've always done things. I wonder if I could ask, what's the biggest opportunity? You guys, more senior, not starting out here. You've seen not just the labs, but other institutions in this country and around the world. What's the biggest missed opportunity, or what is the biggest opportunity that we could take advantage of in new models of collaboration? If you were to sort of wave away the structure of how we do things now and the traditions or the perceived restrictions, what frustrates you in terms of an inability to actually find the best way to work together as opposed to the way that, say, the rules allow? Did I stump you guys? Should we talk about the plans?
Yeah, well, you got me with frustrated. So I'm not sure about. I was going to talk about what I think is exciting. I mean, I think working in the data science space, the opportunities to engage with, this, and I think we're starting to do this. And I'm sure there's work to be done to reduce bureaucratic barriers, but engage with like the many companies that are producing accelerators. To engage with new data sources, the work that we're doing with the Veterans Administration and also, I think, hospitals to apply DOE computing expertise to their problems. It's really exciting. So the fact that we can do that, and perhaps in a way that we weren't able to do previously, is exciting.
Well, I am going to talk about the area of catalysis. I mean, catalysis is a very broad area and that involves the industry, the university, and the national labs. Most of the effort is in the industry because it produces money. But you will find that we have all these tools, nice tools at the synchrotrons in the different DOE complexes, and not many people in the industry actually know how to use these tools. And in some cases, there are not channels that are effective enough to bring the people from the industry to use these tools. And also from the same universities also. You will find that many people, for example, doesn't know that the access as a synchrotron that is supported by the Department of Energy is free. They believe that you have to pay or something like that, and that just stops them for trying to do that kind of experiment. I think that you need to find a way to communicate to the general science community what kind of tools do you have at the labs, and how these tools can be used. I mean, because in many cases, we develop a technique, and that technique is just for the people that is around, the 4 or 5 people that actually knows how to use that technique. And many other people doesn't know that they actually could use the technique because it's part of a synchrotron facility or something like that. So that's open to general users, but they just don't know that. And many people that have very interesting experiments, they just don't try to use that resource. And I think that that's a big issue. And with the industry, in some cases, you have to find a real channel to find a communication between the labs that are supported by the Department of Energy and the industry. Because I think that the industry, many of the problems that we tackle in catalysis, the industry will be really interested in using the facilities that you have in the labs. They will actually could provide money to develop end stations and things like that. So I think that that is a big challenge for the future.
So perhaps in catalysis and batteries and probably other areas, there are opportunities. Is it still working? I broke it. There are opportunities for the labs to serve as a place where data is collated, under appropriate non-competitive regulations, because we need data in order to apply these data science methods.
And you need the support. For example, what you were saying, you are going to acquire tremendous amount of data, but you need the support how to handle that data, how to storage the data, how to handle the data, how to analyze the data. So the lab really needs to have that in place.
Yeah, I guess I would just add that I think there are certain areas where there just collaboration will happen naturally because the interests converge. And I'm thinking of this new area of quantum sensors, quantum computing, AI. That's clearly an area where there's already a tremendous amount of interest and activity out in industry. The interests, the long-term interests are, I think, complementary to those of the basic research community and the labs, but there are clearly ways in which collaboration between the labs and industry in those areas will be beneficial to both. And I think we're starting to see that. And I think the labs, again, just sort of from my narrow view from Fermilab, I think the labs are really pushing in this direction and finding ways to navigate the regulatory thicket to get through this.
Well, I think you said some of the magic words in regulatory thicket. Sometimes when you want to do something that's out of the usual way of doing business, we could need some help with the bureaucracy who isn't used to doing things in a different way.
Mm-hmm. Well, that's kind of what I was getting at. What are the things maybe that you want to try that at the end of the day we can enable? We're just used to doing things in a certain way, and to be fair, to the bureaucracy, the board, folks are busy doing the stuff we're asking them to do in the regular way, and so taking the time to figure out a new way is hard. But if there's a reason to do it, it's on us to make that happen. And there is the real intent, but we need the ideas about what we can change. Well, how about a fun one? What about if I'm jealous of jealous of all of you all, but if you couldn't do the work that you're doing now, if you couldn't be in the field that you're doing now, what are you jealous of? What would you pick if you?
Is another area of science?
It would,
That's what
yeah.
I'm sorry, another area of science. Or if you want to be a fashion model or another.
I'll leave that to someone else. Well, I think that if I didn't do high energy theory, I'd probably do nuclear theory, because both of them have machines where they're discovering new stuff. Your turn.
Well, the traditional answer for me would be sheep farming, I think, coming from New Zealand. But actually, an area that I find fascinating at the moment is neuroscience, trying to understand how the brain, I think we're getting close to the point of understanding how the parts of the brain work, and using that knowledge to both advance fundamental understanding, but also to design new sorts of computational systems. So that would be a really fun area to work in, I think.
Yeah, I think I agree. I think if I wasn't doing astrophysics, I would be attracted to I think biology, neuroscience, genetics. In fact, I have written one paper in bioinformatics. So I'll just take a couple nanoseconds on this. So about 15 years ago, I was in my office working, and I got a phone call out of the blue from a postdoc at, I think it was Rush University Hospital in Chicago. And he was studying the genetics of arthritis, which is an autoimmune disease in mice. And it's a genetically complex disease, so it's not just a single gene. There are multiple genes. And so they had done some gene sequencing to know which genes were associated with arthritis. And he wanted to know if these genes were somehow clustered within the genome. And he had the smarts to realize, okay, clustering. Okay, astronomers, they look at clustering of galaxies. So he literally went to our website, and the first name was the head of our group. He's like, no, he's going to be too busy. So mine was the second name, just alphabetically. So he called me up, and I was like, okay, this is unusual. And so, but a postdoc and I started working with them, and it was really neat. We got to meet the rats. or the mice. And we ended up working together with them on a paper about clustering of arthritic genes in mice, and applied a lot of the techniques that we had been using to study galaxies in the Sloan Digital Sky Survey to arthritis. Now, I have no idea whether this paper had any impact at all in genetics and biology. I've always meant to go back and look if there were like any citations at all. But it really sort of opened up. But for a few months, the postdoc and I were like, "Oh, gee, this is really cool. Maybe we were going to download like at that time the human genome, I think, was just becoming public, and we thought, okay, maybe let's do a big study of this." And so I could see, if I wasn't doing this, I can see other areas where we could apply the same kind of tools we use in a completely different area, and that would be exciting.
So I think my answer would be somewhere in the biophysics, biochemistry realm. And I've always been interested in how do things work, and I think we now have some fantastic tools for imaging that we can actually watch processes go on. That was not possible when I was trying to figure out what to do when I was in college. So I think I would go back and try to learn more about how we work. Not that I'm not still totally fascinated with how particles work, but I think that would be the other way I'd go.
I think that I will be doing imaging. If I will not be doing catalysis, I will be doing imaging and how you process images and all of that, all the way from the microscopic world to the galaxies and things like that. I find that that's a fascinating area. I mean, really, really.
I just have to say I'm disappointed that none of you said astrophysics.
Will we handle your images, man?
I would have been accused of some adult onset disease.
We might be done. Okay, well, thanks a lot. This has been fun, and I think we are. What is next?
So next, actually, what I'd like to do is I'd like to invite the program representatives to actually stand and be recognized, because I know a lot of you worked very hard, for this particular opportunity, and we're going to be then taking pictures, and so that's going to take some amount of time. So I hope that the program representatives will also come up and take pictures. So at this point, I think that we'd like to thank everyone. Certainly, the event is being live streamed, so you can go back and watch it. I think folks at your laboratories will be very proud. Certainly, we thank you for your contributions to science and for the department. We certainly thank the lab directors for nominating you. We look forward to another very competitive set of nominations next year. So thank you, everyone, for coming.
Rick, did we say anything wrong? We're live streamed. Are we okay? No more. No more. Okay. It was fun. I don't even.
Can I get a group shot of you all?
Yeah. How would you like us to?
If you would stand just
Behind the beautiful plants.